Today we're tackling something pretty fascinating. How do we actually get a handle on dynamic graphs?
Yeah, it's a big challenge.
Think about, say, your professional network on LinkedIn, right? It's always changing, new connections, new jobs, new projects, or maybe global supply chains constantly shifting.
Mm-hmm.
Representing these kinds of, well, living structures in a useful way is a real puzzle.
Absolutely. And it's not just about seeing them as like snapshots frozen in time. That really misses the point.
Right.
We need models that can grasp the continuous evolution, the subtle shifts in how things are connected, the changing importance of nodes over time. That's key for predicting things accurately and getting real insights.
Exactly. And for this deep dive, we've managed to get our hands on some really interesting, cutting edge research. It all comes together in this recent paper called DyGSSM, Multi-view Dynamic Graph Embeddings with State Space Model Gradient Update.
Catchy title.
Huh, yeah. So our mission today is basically to unpack the core innovations in DyGSSM. We want to understand what makes it different and why it might be a significant step forward.
Sounds good. Where should we start?
Let's start with the basics. What were the main problems, the limitations with how people used to try and model these dynamic networks?
Well, one of the biggest issues with a lot of the older methods is that they tended to treat a dynamic math as just a sequence of separate static snapshots.
Okay, like looking at individual frames of a movie instead of watching it play.
Precisely. You lose the flow, the transitions between those frames. And within each snapshot, these methods often struggle to capture both the sort of immediate neighborhood, the local structure, and the bigger picture, the global structure, at the same time.
Interesting. Can you give me an example? What's the difference between that local and global view, and why does getting both at once matter so much?
Sure. Think about a social network again. Your local view is your direct friends, right? Who you talk to regularly.
Uh-huh.
Methods like GNNs, graph neural networks, they're actually very good at analogizing these local areas using something called message passing. Nodes share info with their neighbors,
Okay.
but if you only look locally, you might miss, say, how different groups are influencing each other across the network or broader trends. That's the global view.
Right.
Now, other techniques may be using random walks. They wander further across the graph, giving you more of that global sense. But the tricky part was many older approaches were good at one or the other within a single snapshot, but not really both simultaneously.
I see. So it's like needing both the magnifying glass and the wide-angle lens at the exact same moment.
That's a good analogy, yeah.
Okay, so that's one big challenge. What was the second hurdle DyGSSM aimed to clear?
The second major limitation is really about how these models learn over time, how they update their parameters, their understanding of the graph.
How so?
Well, many approaches would sort of adjust themselves based on how well they did recently, maybe just looking at the last snapshot or two. Think of something like WinGNN. It mainly uses adjacent time steps to update.
Which sounds okay for short-term stuff.
It can be, yes, but it might totally miss longer term patterns or cycles. It's like trying to predict the stock market just by looking at yesterday and today. You'd miss the bigger economic waves.
Yeah, definitely.
So these methods often lacked a robust way to kind of, remember the important history and adapt their learning based on performance across a longer sequence of graph states. They might even get thrown off by one bad snapshot.
Okay, got it. So two key problems. Getting local and global views together in each snapshot and managing learning effectively over time. How does DyGSSM tackle these? What's their big idea?
DyGSSM's first really key innovation is what they call a multi-view approach. The core idea is simple but powerful. Capture both local and global features concurrently within each snapshot.
Okay, multi-view. Like having two cameras running at the same time.
Sort of, yeah. Two complementary perspectives feeding into the model's understanding at every single point in time.
So tell me more. How do they actually generate these two views? What's the mechanism for the local view?
For the local side, they use graph convolutional networks, GCNs, like we mentioned.
Right, the message passing one.
Exactly. They excel at pulling out these local node embeddings by letting nodes gather info from their immediate neighbors. It gives a really detailed picture of the node's direct surroundings.
Okay, makes sense. And the global view, how do they get that wider perspective within the same snapshot?
That's where they use something called biased random walks. Imagine starting at a node and taking lots of short walks across the graph.
Like exploring?
Kind of, yeah. But the walks are slightly biased to encourage exploring beyond just the immediate friends, sampling a wider chunk of the network structure. They actually specified the parameters, setting a bias parameter to 2, running 50 walks of length 5 from each node, and then focusing on the 5 most frequently visited nodes in those walks.
Okay, so it's a structured way of exploring further out.
Right. And these walks generate sequences of nodes for each starting node. These sequences then get fed into GRU's gated recurrent units.
GRUs, those are neural networks for sequences, right? Like text.
Exactly. They're designed to find patterns in sequences. Here, the GRU processes the random walk sequences to figure out a node's global importance, its reach across the wider graph. They even developed a light GRU version to make it scale better for massive networks.
Clever. So you end up with two different embeddings for each node, one local, one global. How do they put them together?
Ah, that's the next clever bit. They use a cross-attention mechanism.
Okay. What does that do?
Think of it like this. The local embedding acts as a question, a query. It essentially asks the global embedding, okay, based on who I'm directly connected to right now, what parts of the broader network information are most relevant to me?
Ah, I see. So it wastes the global information based on the local context.
Precisely. It lets the model dynamically decide how much importance to give different global features depending on the specific local situation each node. It leads to a much richer, more context-aware final representation.
That sounds really powerful for getting a nuanced picture. Okay, so that covers the multi-view part. What about the second big innovation, handling the learning over time, the temporal dependencies?
Right. This, I think, is where DyGSSM gets really novel. They use a state space model, an SSM, specifically for managing how the model updates its parameters based on gradients during training.
A state space model. Okay, that sounds advanced. Break that down a bit. How does it help the model learn from its history better than just looking at the last couple of snapshots?
Okay, so fundamentally, after each snapshot, the model calculates its error, the loss. Now, here's the key. The gradient of that loss, which tells the model how to adjust itself, is weighted.
Weighted how?
Based on performance, if the model did well on that snapshot, low error, the gradient gets a higher weight. If it did poorly, the gradient gets a lower weight.
So it learns more from its successes on specific snapshots?
Kind of, yeah. It pays more attention to the signals from times it was performing well. And this weighted gradient is then fed into the state space model.
And what does the SSM do with that?
The SSM acts like a sophisticated memory system. Crucially, they initialize it using something called the HiPPO algorithm, high-order polynomial projection operators.
HiPPO.
Yeah, it's a way to set up the SSM so it's really good at compressing and remembering the important information from a sequence over long periods. It helps the SSM preserve the relevant history from the sequence of weighted gradients it receives.
So the SSM, powered by HiPPO, lets the model effectively remember useful patterns from past snapshots and forget noisy or less relevant ones when it updates its main parameters.
That's the core idea. It allows for a much more informed, history-aware update process compared to just looking at immediate neighbors in time.
That makes a lot of sense. And you mentioned they use an overlapped sliding window for training too. How does that fit in?
Right, so instead of just processing snapshot 1, then snapshot 2, then 3, they use a window, say snapshots 1 through 5. They train on that window. Then the window slides forward maybe to snapshots 2 through 6.
Okay.
Because the windows overlap, each snapshot contributes to the learning process multiple times in slightly different contexts. This helps capture longer dependencies and makes the training more stable. It connects back to the SSM needing a sequence of inputs to work effectively.
This all sounds very well thought out theoretically, but did it actually work? How did they test DyGSSM?
They did pretty extensive testing. The main task was link prediction. Can the model predict future connections in the graph based on its history?
A standard benchmark.
Exactly. They used 5 common real-world datasets, 2 Bitcoin transaction networks, Alpha and OTC, a research collaboration network, DPLP, and 2 social networks, Reddit, Tidal, and UCI. So a good mix.
And the results, did DyGSSM live up to the hype?
Well, the results were definitely strong. Both DyGSSM and the light DyGSSM version consistently outperformed a range of other state-of-the-art dynamic graph methods on these datasets.
Consistently is good. Anything particularly stand out?
Yeah, one really interesting finding was that the improvements were often more pronounced on datasets that had a larger number of snapshots, a longer history.
Ah, suggesting that the SSM part, the temporal modeling, really shines when there's more history to learn from.
That's exactly the interpretation. It seems to directly validate their hypothesis about the SSM being effective at capturing those longer range dependencies. More data over time lets that mechanism show its strength.
Did they try to isolate the effect of the SSM?
They did. They ran an ablation study, basically turning off different parts of the model to see what happened. On the UCI dataset, when they removed the SSM component, performance dropped noticeably, especially in ranking metrics like MRR and recall at 10.
So that confirms the SSM is really doing critical work.
It strongly suggests it, yes. They also found that using a random window size instead of their sequential overlapping one hurt performance too, backing up that aspect of their training approach.
Okay, so it really seems like the magic is in that combination. The multi-view approach getting local and global structure right within each snapshot, and then the SSM with HiPPO managing the learning across snapshots in a history-aware way.
That's absolutely the key takeaway, I think. It's the synergy between those two core innovations that seems to give DyGSSM its edge. It addresses those two fundamental limitations we talked about earlier.
Fascinating stuff. So just to quickly recap the big innovations here. First, the concurrent multi-view embedding GCNs for local biased random walks plus GRUs for global, fused with attention.
Right.
And second, the temporally aware gradient updates using the state space model, initialized with HiPPO, fed by performance-weighted gradients over a sliding window.
You got it. It moves beyond just seeing snapshots in isolation and learns the deeper evolutionary patterns.
It really feels like a more holistic way to understand these networks that are constantly in motion.
I agree. It allows for learning more nuanced and persistent dynamics.
And it looks like they're already thinking about next steps, like applying this to continuous time dynamic graphs, where changes aren't just locked to discrete snapshots.
Yeah, that's a really exciting frontier. Many real-world systems don't change neatly at fixed intervals, so handling that continuous flow is a major goal.
Well, this has been a really illuminating deep dive into DyGSSM. It's pretty amazing to see how these sophisticated mathematical tools are being used to get a better grip on such complex, evolving systems.
It really is.
It kind of leaves you wondering, given DyGSSM's ability to sort of remember and leverage history to guide its learning, what other kinds of complex dynamic systems, maybe even things outside of mimical networks, could benefit from similar approaches? Something to chew on. Thanks for joining me for this deep dive.